Powered flight, born of the Wright brothers' genius and dedication. It would change the world. The secret of the Wright brothers' success was that they appreciated that what made wings produce lift could also be used to generate thrust. The pioneers flew by the seat of their pants as they sought a better understanding of aerodynamics. And propellers of many shapes and sizes proliferated. Their development soon spurred by the desperate struggle for airborne supremacy in the Great War. A propeller's efficiency is a measure of its effectiveness at converting engine power into propulsive thrust. But how to achieve it? How big should they be? And how many blades should they have? Should they push? Pull? Or do both? With peace came an insatiable demand for the speed, comfort, and the sheer excitement of air travel, together with ambitious couplings of engines and propellers. The Handley Page 42 provided a regular and reliable service to the Empire. The Dornier DOX, 12 engines, 12 propellers, but still underpowered. Nevertheless, it was the largest aircraft of its time. Impressive civilian enterprise, disrupted once again by global military conflict. Demand for higher performance brought more power, more blades, and better pitch control. Like men, propellers matured quickly. Contra-rotating systems finally came of age. Peace again, and by the end of the 1940s, all the basic technology of the propeller we know today had been introduced. Nowadays, propellers are taken for granted. But how do they work? It's important to know, because they produce effects that influence aircraft behavior and the way we fly them. Remember that the Wright brothers appreciated that the basis for propeller design was the same as for wings, the subsonic aerofoil. When moving through the air, it generates a total reaction, which enables an aircraft to fly. This is best explained by looking at it in terms of the lift produced by the aerofoil and the drag created by its resistance to the air. If the angle of attack is increased, more lift is generated, but at the expense of increased drag. Maximum lift being produced at the point of stall. A wing is usually at its most efficient at a relatively small angle of attack. In very simple terms, a propeller or air screw is really two or more rotating aerofoils set to pull the propeller through the air, in the same way as the thread of a screw pulls it into wood. During flight, its motion will comprise rotational velocity and forward velocity. With the propeller stationary, any forward velocity is that of the aircraft, the true airspeed. But a rotating propeller accelerates air and produces the induced flow. The sum of the TAS and the induced flow is the total inflow. Now the direction of the relative airflow can be plotted. But we know that to work effectively, aerofoils have to be set at a small angle of attack. The angle between the chord line and the plane of rotation is known as the blade angle or pitch of the propeller. The rotational velocity at the blade tip is faster than near the hub. And if the pitch remained constant, the angle of attack would increase towards the blade tip, possibly causing it to stall. So the blade is twisted to maintain a constant angle of attack. This is a fixed pitch propeller. It generates a total reaction in the same way as a wing. We know that the amount of lift generated varies with the angle of attack. It also varies with the speed of the airflow. The faster the airflow, the greater the lift. And vice versa. So in order to maintain level flight, when pilots alter an aircraft's speed, they also have to adjust the angle of attack to keep the lift constant and equal to the aircraft's weight. But whereas the speed of the airflow over a wing aerofoil is dictated by the speed of the aircraft, the airflow over a propeller is governed by its rotational speed, which is much faster than the forward velocity and virtually constant. Consequently, changes of forward velocity have very little effect on the speed of the relative airflow. What is affected by changes of forward velocity is the angle of attack and the consequent strength and direction of the total reaction produced. Remember that the total reaction produced by a wing aerofoil can be resolved in terms of lift and drag, and that the penalty for increased lift is increased drag. With a propeller, the total reaction is resolved as thrust, the force needed to overcome the drag of the airframe, and the propeller drag, or torque, which balances the power output of the engine. The penalty for increased thrust is increased torque. When a propeller is turning at a constant speed and the aircraft is stationary, the angle of attack is big, and large amounts of thrust and torque are produced. As the aircraft accelerates, so the angle of attack decreases with a consequent loss of thrust and torque. This continues until the reducing thrust equals the increasing airframe drag, when the aircraft has reached its maximum speed. The principal limitation of fixed-pitch propellers is that there is only one speed at which they work at peak efficiency. This propeller is a fine-pitch propeller, giving good performance for takeoff and climbing, but a relatively low maximum speed. By increasing or coarsening the pitch, the maximum speed can be increased. But there are practical limits to the size of the blade angle that can be used, since too large an angle might mean the propeller could be stalled when the aircraft is stationary or moving at low speeds. Torque would be high, so RPM would be low, and because the direction of the total reaction is further from the direction of flight, less thrust would be produced, and acceleration would be too slow for takeoff from normal airfields. The pitch of this propeller is very coarse. For the Supermarine S-6B was built to win the Schneider Trophy, and speed was all that mattered. But takeoff acceleration was very sluggish. So, like a duck, it took to the water for a runway of unlimited length. During World War II, propeller designers faced many problems as they strove to satisfy the requirement for fighters with high-speed performance, short takeoff runs, and rapid rates of climb. The answers came quickly. Initially, the Spitfires and Hurricanes fixed-pitch propellers were replaced by two-pitch propellers. Fine pitch was selected to give a suitable angle of attack for takeoff and climb, then changed to coarse pitch for cruising and high speed. Though superior to fixed pitch, there was still a large sector of the speed range where the propeller was not operating efficiently. A further drawback to both fixed pitch and two-pitch propellers is that because their rotational velocity is governed not only by the power setting of the engine, but also by the aircraft's speed, pilots must be careful not to over-rev engines in steep dives. This problem was eliminated in Spitfires and Hurricanes by converting their two-pitch propellers to variable pitch units shortly prior to the Battle of Britain. This also shortened takeoff runs, increased rates of climb, significantly improved maneuverability, and lifted their operational ceilings. The introduction of variable pitch enabled the propeller to work close to its maximum efficiency over a wider speed range. With a variable pitch propeller, a constant speed unit automatically adjusts the blade angle to maintain a constant loading on the engine. The selected propeller RPM remains the same, regardless of engine power variations and airspeed. However, a potential problem was created. If the engine failed, the rotational velocity would start to decrease, and the constant speed unit would reduce the blade angle to try to maintain the RPM until the blade reached the fine pitch stop. Now the relative airflow strikes the forward surface of the blade, creating a negative angle of attack and reversing the torque so that the propeller drives the engine. This is known as windmilling. The decrease in performance it causes will reduce the gliding range, and if the engine is damaged, continuing to turn it could cause it to seize or even catch fire. Improvements to the variable pitch propeller enabled it to be feathered by turning it into a position of zero torque to stop the engine turning and minimize the drag. A tactical landing. The bulk of a Hercules brought to a halt in about 750 meters, and the pilot wasn't trying too hard. Reverse thrust, a further development in pitch control, not only brought dramatic improvements in braking, it also enabled aircraft to be reversed using their own power, and made maneuvering on the ground far easier. Reverse thrust is produced by turning the blades past the flight fine pitch limit to create a relatively large negative angle of attack. But to return to World War II and another problem facing propeller designers. How to develop them to absorb the ever-increasing power outputs of the engines. Propellers must be able to absorb engine power, otherwise they'll just spin faster to no effect. The answer is to increase the area of aerofoil surface. There are two ways of doing this. Firstly, the diameter can be increased. This enables an efficient high aspect ratio blade shape to be maintained, but increases the tip velocity, which is of critical importance, since compressibility effects at transonic and supersonic speeds greatly increase drag, which reduces the propeller's efficiency. Another way is to increase the propeller's solidity, which is the proportion of the propeller disc filled by the blades. But increasing the chord reduces the blade's aspect ratio and its efficiency. So designers opted to increase solidity by adding more blades. During late 1939, the Spitfire's two-bladed propeller was replaced with a three-bladed model. In 1942 came the Mark IX, with its 4-bladed propeller. And the final Spitfire Marks were equipped with 5-bladed propellers, in common with many other fighters of the day, which was the maximum number that could be fitted to the hubs at that time. But when still more powerful engines were developed, the designer's solution was to use contra-rotating propellers. The diameter of the B-36's propellers was a massive 19 feet, because on load-carrying aircraft, larger propellers had to be used. But the stresses of their blade roots can be enormous, as much as 22 tons. Three principal stresses affect propellers, and centrifugal force causes 2 of them. The first is produced by the radial component, which tries to tear the blades from the hub, and the second by the tangential component, which tries to turn the blades to find the pitch. The centrifugal twisting moment. The third principal stress is generated by the total reaction, which tries to turn the blades in the opposite direction, the aerodynamic twisting moment, which reduces the effect of the centrifugal twisting. But if the propeller is windmilling, this aerodynamic twisting will be reversed. So at high speeds, the combined stresses could overwhelm the pitch-changing mechanism and make it impossible to feather the propeller. Propellers also affect the handling characteristics of aircraft on the ground, particularly during the takeoff run, when they produce effects that try to swing the aircraft to one side. Ignoring crosswinds, there are 4 causes for this, but only 2 of them affect aircraft with nose wheel landing gear. The first of these is produced by the torque reaction to the rotating propeller, which tries to roll the aircraft in the opposite direction, lifting the starboard wheel and forcing the port wheel down. Consequently, the rolling resistance of the port wheel is greater than that of the starboard wheel, and this imbalance creates a tendency for the aircraft to yaw to port until the wheels lift off. The second cause of swing during the takeoff run is produced by the propeller's spiraling slipstream and the resultant asymmetric airflow over the fin and rudder. This generates an aerodynamic force which tends to drive the fin to starboard and the nose to port. There are 2 more causes of swing during the takeoff run, but these only affect aircraft with a tail wheel. Obviously, the RPM of an upgoing blade is the same as that of a downgoing blade, and in level flight, the distance they travel in half a revolution, their relative airflows, and their angles of attack will be equal. But the beginning of the takeoff run will be in a tail-down attitude, when the axis of rotation is no longer the same as the horizontal path of the aircraft. This produces the asymmetric blade effect. Now the downgoing blade has to cover a greater distance than the upgoing blade in the same time, so its relative airflow is faster. Similarly, the angle of attack of the downgoing blade is greater than that of the upgoing blade. Therefore, the downgoing half of the propeller will be generating more thrust than the upgoing half, which will tend to yaw the aircraft to port until the tail wheel is raised and the propeller's axis of rotation is brought into line with the aircraft's horizontal path. The second cause of swing on takeoff, exclusive to aircraft with a tail wheel, is the gyroscopic effect. The force applied to the propeller as the tail wheel lifts off acts as though it is applied 90 degrees in the direction of rotation and produces a swing to port. Of course, in aircraft whose propellers rotate in the opposite direction, all these effects will be reversed, and those fitted with contra-rotating propellers will experience none at all. Today, propellers remain a very efficient means of aircraft propulsion, and their performance is superior to pure jets or turbojets at low subsonic speeds and medium altitudes. The advent of composites has enabled lighter, stronger blades with improved aerofoil sections to be manufactured. Nowadays, propellers are not only used to produce thrust, like these giant 21 feet diameter examples, but also to absorb energy to generate electrical power. Wind farm propeller diameters can be as much as 60 meters. What next? Who can tell? Could those who believed that jet propulsion would sound the propeller's death knell have envisaged an aircraft like this? With propellers producing lift for vertical takeoff, then turned through 90 degrees to provide thrust for conventional flight? Or like this, the prop fan, designed to satisfy the demand for greater fuel economy and reduced noise footprints. Propellers are older than powered flight, yet like the aircraft they propel, their development will continue to surprise, spurred by the application of new technologies. Strangely, since the birth of powered flight, one question remains unresolved. Should propellers push, pull, or do both? Clearly, the matter will be the subject for aerodynamic debate for years to come.